Around 540 million years ago, Earth was a very different planet. The continents were mostly empty rock. No forests covered the land. No insects filled the air. No animals walked across the ground. Almost all complex life lived in the ocean, and for a long time, that ocean was relatively quiet. Many early creatures drifted slowly through the water or rested along the seafloor. Few chased anything. Then something changed. In a surprisingly short stretch of geological time, the oceans became far more dangerous. Eyes suddenly appear in the fossil record. Hard shells begin to form. Bodies develop muscles built for movement. For the first time in Earth's history, animals begin hunting other animals. Predators emerge. Prey respond. Armor spreads across soft bodies. Spines grow where none existed before. Creatures evolve strange shapes that have no true equivalent in the modern ocean. Some animals carry multiple eyes across their heads. Others swim using rows of rippling flaps along their sides. Some develop heavy protective armor long before bones appear inside their bodies. Evolution begins experimenting in ways the planet had never seen before. Nearly every major animal group alive today traces part of its ancestry back to this ancient moment. And yet many of the strange rulers of those early seas eventually vanished, leaving only fragments of their story buried in ancient rock. So what kind of ocean allowed life to invent so many new designs so quickly? Why did predators, armor, and complex vision appear almost all at once? And what forces eventually erased most of these bizarre pioneers of animal life? Today, we descend into the Paleozoic Sea, a world where evolution first learned how to hunt. Before we continue our journey into these ancient oceans, I have a quick question for you. What kind of place are you listening from right now? Home, work, school, or somewhere completely unexpected? And I would also like to express my sincere gratitude to our Patreon supporters, whose generosity helps make these videos possible. Now let's continue. A stillness once covered the planet so completely that movement itself felt like a rare and fragile event, as if the surface of the world had not yet learned how to stir. Beneath a dimmer sun, the ocean stretched without interruption, a vast and quiet expanse where life existed, but did not yet rush, chase, or resist. It simply persisted. For an immense span of time, life remained small, simple, and almost invisible to the rhythms that would later define the sea. Single-celled organisms drifted through the water, carried not by intention, but by gentle currents that required no effort to follow. These microscopic forms absorbed energy, divided, and continued, repeating a pattern that endured for ages beyond easy imagination. There was no urgency in their existence, no need for speed or defense, only a slow and steady continuity. Gradually, something more intricate began to take shape. Soft-bodied organisms appeared along the seafloor, pressing themselves into the sediment like faint impressions of thought rather than fully realized creatures. These early forms, often grouped within what would later be called the Ediacaran life, displayed shapes that felt unfamiliar even by ancient standards. Some resembled fronds that swayed gently in place, anchored yet flexible, while others lay flat against the ocean floor, their bodies patterned with repeating segments that hinted at organization without revealing true complexity. The absence of hardness defined this world. No shells protected these organisms, no rigid structures gave them strength or permanence. Their bodies were delicate, composed of tissues that left only subtle traces behind. Movement, when it occurred, was slow and minimal, more like a shifting presence than an act of locomotion. The seafloor remained largely undisturbed, untouched by burrowing or digging, preserving a smooth and undisturbed landscape where life rested rather than reshaped its surroundings. Above them, the chemistry of the ocean was quietly transforming. Oxygen, released over countless generations by photosynthetic organisms, began to accumulate in the water and the atmosphere. This change did not arrive as a sudden shift, but as a gradual enrichment, altering the conditions under which life could exist. With more oxygen available, the potential for energy increased, though the organisms of this time had not yet learned how to fully use it. The delay between possibility and transformation stretched across ages. Complexity did not emerge simply because conditions allowed it. It required interactions, pressures, and opportunities that had not yet aligned. Without predators, there was little need for armor or speed. Without competition, there was no urgency to innovate. Life remained in a state of quiet sufficiency, shaped more by stability than by challenge. And so the ocean held its calm. It nurtured forms that lived without fear, without pursuit, without resistance. Beneath that still surface, however, the slow accumulation of oxygen and the subtle changes in chemistry continued, preparing conditions that would one day support a different kind of existence. The foundations were being laid, not through sudden invention, but through patience, as if the sea itself was gathering the elements needed to begin something far more dynamic. Change did not arrive as a single event, but as a gathering pressure that finally found release, like a breath held far too long beneath the surface. Over a relatively brief span of geological time, the quiet patterns that had defined life began to fracture, giving way to a surge of forms that carried structure, motion, and intent in ways the ocean had not yet expressed. The transformation unfolded within sediments that would one day be known as the Burgess Shale, where layers of fine mud preserved the delicate outlines of this sudden expansion with remarkable clarity, capturing bodies that seemed to arrive fully formed from a long period of restraint. Shapes multiplied, not gradually, but in a burst of variation that filled ecological space almost as quickly as it appeared. Organisms developed distinct front and back ends, a directional sense that allowed movement to become purposeful rather than passive. Bilateral symmetry established a new kind of organization, aligning sensory structures and locomotion along a central axis. This shift brought coherence to bodies, making motion more efficient and interactions more precise, as if life had discovered a more effective language for navigating its surroundings. Segmentation followed, dividing bodies into repeating units that could specialize or coordinate, creating flexibility without losing control. This modular design allowed certain regions to adapt for movement, others for feeding, and still others for sensing the environment. It introduced a rhythm to anatomy, a pattern that could be modified and refined over time, offering evolution a framework upon which complexity could build. Limbs, appendages, and specialized structures began to emerge from these repeating segments, each variation testing a new possibility within the expanding landscape of forms. Within these bodies, another quiet revolution unfolded. Networks of nerve cells became more organized, linking sensation to response with increasing speed and coordination. Primitive nervous systems began to integrate signals from the environment, allowing organisms to react in ways that were no longer purely chemical or diffuse. Movement gained timing, direction, and adjustment, creating interactions that unfolded over moments rather than drifting across hours. The ocean was no longer a place of simple presence, but one of awareness, however faint and early that awareness remained. As these capabilities accumulated, relationships between organisms began to shift. Feeding became more selective, encounters more consequential. Some forms developed structures suited for grasping or tearing, while others responded with thicker coverings or altered shapes that reduced vulnerability. This interplay marked the beginning of an evolutionary arms race, a continuous exchange of adaptation and counter-adaptation that would shape life from that point forward. Each advantage carried the seed of a response, and each response introduced new pressures that drove further change. The fossil record of this interval reveals not only diversity, but experimentation. Body plans appeared that would endure for hundreds of millions of years, alongside others that would vanish entirely, leaving only brief impressions in stone. The ocean became a place where innovation unfolded rapidly, guided by the interplay of structure, function, and environment. In this acceleration, the foundations of modern animal life took form, establishing patterns that would echo through every era that followed, even as the details continued to change. It began with the ability to see, not as a faint sensitivity to light, but as a structured perception that could resolve shape, distance, and motion with clarity. In a world that had only recently learned how to organize its own bodies, this new sense introduced a different kind of presence, one that could detect, track, and anticipate. Among the many forms emerging in these waters, one stood apart, not through size alone, but through the way its entire body seemed arranged around the act of pursuit. Anomalocaris moved with a fluid precision that contrasted sharply with the slower, more deliberate motions that had defined earlier life. Its body extended into lateral flaps that undulated in sequence, producing a steady propulsion that allowed it to glide rather than drift. This method of movement offered control without rigidity, enabling subtle adjustments as it navigated the layered spaces of the water column. It was neither anchored nor aimless, but directed, its path shaped by perception and intent. At the front of its body, a pair of compound eyes rose on short stalks, each composed of thousands of individual lenses. These eyes did not merely register light, they assembled it into a detailed image, capturing contrasts and edges that revealed the outlines of other organisms. Movement could be detected quickly, even at a distance, allowing Anomalocaris to orient itself with accuracy. This level of visual resolution transformed the surrounding environment from a diffuse field into a landscape filled with distinct targets and pathways. Beneath these eyes, two flexible appendages extended forward, lined with spines that curved inward. These grasping structures moved independently yet in coordination, capable of sweeping through the water or closing around softer bodies with controlled force. They functioned as both sensors and tools, testing resistance, adjusting grip, and guiding prey toward the center of the body. Their design reflected a balance between strength and dexterity, allowing interaction with a range of forms that varied in size and texture. At the core of this arrangement lay a circular mouth composed of overlapping plates, arranged in a pattern that formed a ring of hardened surfaces. Rather than cutting in a single direction, this mouth applied pressure from multiple angles, compressing and breaking down tissue through repeated motion. It was an architecture suited for processing rather than slicing, capable of handling organisms that lacked rigid protection. Each component of the body contributed to a sequence that began with detection, continued through capture, and ended with consumption. The presence of such a creature altered the conditions of the ocean in ways that extended beyond its immediate actions. Vision introduced distance into interaction, allowing encounters to occur before contact, shaping movement and positioning across space. Organisms that could be seen could also be avoided or pursued, creating a dynamic in which visibility itself became a factor in survival. In response, some forms began to adjust their shapes, their behaviors, or their timing, shifting away from open exposure toward more concealed or protected ways of existing. This marked a transition in how life related to its environment. The ocean was no longer defined solely by chemical gradients and passive encounters, but by active relationships between organisms that could sense and respond to one another in real time. The emergence of a predator like Anomalocaris, did not simply add another participant to the ecosystem, it restructured the interactions within it, introducing a layer of complexity that would continue to deepen as new adaptations followed. Across the seafloor, a subtle transformation began to appear in the texture of life itself, as bodies that had once yielded easily to pressure started to resist it. Surfaces grew firmer, layered with minerals drawn from the surrounding water, forming protective coverings that altered both shape and function. Among the most widespread of these forms were the trilobites, their bodies divided into articulated segments and shielded by a hardened exoskeleton that reflected a new relationship between organism and environment. This outer structure was not merely a barrier, but a framework that supported movement while offering defense. Trilobites could enroll their bodies, curling into a compact form that reduced exposed surfaces, their rigid plates fitting together with precision. The mineral composition of these exoskeletons, often reinforced with calcite, provided durability that soft tissues could not achieve, allowing them to withstand pressures that would otherwise damage or destroy. Their presence across a wide range of habitats suggested that this strategy offered a clear advantage in a sea that was becoming increasingly interactive. Elsewhere, other organisms followed similar paths, developing shells that encased their bodies in layers of calcium carbonate or other minerals. These coverings varied in thickness and structure, some smooth and rounded, others ridged or ornamented, each variation reflecting a balance between protection and mobility. The ocean, once defined by softness, began to display a mosaic of hardened forms, each one testing how much resistance could be maintained without sacrificing function. In response to these defenses, feeding structures began to change as well. Organisms that relied on consuming others adapted their methods, applying greater force or altering the way they interacted with their surroundings. Evidence of these interactions remains preserved in the fossil record, where trilobite shells bear small fractures, punctures, or repaired damage that indicates survival after attack. These marks are not random, but patterned, suggesting repeated encounters that shaped both predator and prey over time. Spines emerged as another layer of defense, extending outward from bodies in arrays that increased apparent size and made handling more difficult. Some organisms developed long, delicate projections, while others grew shorter, sturdier spines that reinforced their overall structure. These features did not prevent interaction entirely, but they altered its outcome, forcing predators to adjust their approach or select different targets. Each modification introduced a new variable into the ongoing exchange of adaptation. This gradual escalation did not unfold as a single event, but as a continuous adjustment across generations. As protective features improved, methods of overcoming them evolved in parallel, creating a dynamic in which no single advantage remained absolute for long. The interplay between armor and feeding strategies established a pattern that would persist throughout the history of life, shaping not only individual organisms, but entire ecosystems. The ocean became a place where form and function were closely linked to interaction, where the structure of a body reflected both its needs and the pressures it faced. Hardness, once absent, became a defining characteristic of many lineages, leaving behind a fossil record that captured these changes with clarity. Within these preserved remains, the marks of contact, resistance, and survival reveal a world in which life was no longer simply present, but engaged in a continuous process of adaptation that reshaped the possibilities of existence. Some forms from this era seem less like steps toward the familiar and more like brief departures into possibilities that were never repeated. as if evolution explored directions that did not need to lead anywhere lasting. In the fine layers of ancient sediment, certain bodies appear so unusual that they resist easy comparison, carrying arrangements that feel assembled without precedent or continuation. Opabinia drifts into view with a structure that does not settle into expectation. Along the front of its head, 5 eyes are arranged in a loose arc, each positioned to gather a slightly different perspective of the surrounding water. This arrangement does not unify vision into a single forward gaze, but instead creates a broad field of awareness, a scattered perception that overlaps and blends. Beneath these eyes extends a flexible proboscis, a soft appendage ending in a grasping tip, capable of reaching outward, curling, and drawing material inward toward the mouth, hidden beneath the head. Its body moves with gentle undulations, neither hurried nor still, navigating its environment in a way that reflects coordination without urgency. Nearby, hallucigenia presents a form that appears inverted at first glance, its orientation uncertain until studied more closely. Along one side of its elongated body rise a series of rigid spines, projecting upward like a row of narrow towers. Beneath, softer appendages extend downward, functioning as limbs that support slow movement across the sea floor. Its head is small and understated, lacking the prominence seen in other organisms, while its body carries the more striking features. The contrast between vulnerability and defense is built directly into its shape, as if protection and exposure coexist in a single design. These organisms represent a period when evolutionary pathways were not yet narrowed by long histories of refinement. Genetic variation produced a wide range of anatomical experiments, each one interacting with the environment in its own way. Without the constraints imposed by later ecosystems, forms could persist even if they were not optimized by future standards. The ocean held enough space, enough resources, and enough variability to support structures that would later be replaced or forgotten. Many of these designs left no descendants. Their lineages ended quietly, preserved only in fossil impressions that capture a brief existence within a much longer narrative. The absence of modern equivalents does not suggest failure in a simple sense, but rather reflects a process of selection that favored certain patterns over others as conditions continued to change. Features that did not integrate well with emerging ecosystems, or that could not adapt to new pressures, gradually disappeared. At the same time, the presence of such diversity reveals how open the possibilities once were. Body plans that seem improbable today were once part of a living system, interacting, feeding, and reproducing, alongside more familiar forms. The boundaries of what life could become had not yet been defined, allowing for combinations that would later be constrained by competition, efficiency, and stability. As these unusual organisms moved through their environment, they contributed to a broader tapestry of experimentation, each one testing how structure could support existence under shifting conditions. Their disappearance did not erase their influence entirely, as the processes that produced them continued to operate, shaping new forms in more restrained directions. The memory of these designs remains embedded in stone, offering a glimpse into a time when life explored its possibilities with a freedom that would gradually give way to more established patterns. In certain stretches of the shallow sea, life began to gather not just in numbers, but in structure, forming communities that rose gently from the seafloor and altered the flow of water around them. These early constructions did not resemble the vibrant reefs of later ages, yet they marked the first time organisms collectively shaped their environment into something layered and persistent. The architects of these formations were small, porous creatures known as archaeocyathids, their bodies composed of double walls perforated by tiny openings through which water passed in a constant, quiet exchange. Each individual remained fixed in place, anchored to the substrate, filtering microscopic particles from the surrounding water. Over time, their skeletal remains accumulated, stacking and merging into frameworks that extended outward and upward. As generations lived and died, these structures thickened, creating irregular mounds and ridges that provided both shelter and surface for other forms of life. The reef became less a single organism and more a shared construction, built slowly through repetition and continuity. Among these frameworks, early relatives of corals began to appear, contributing additional layers of calcium carbonate that strengthened and diversified the growing formations. Their presence introduced new textures and spaces, small cavities and overhangs where water slowed and particles settled. These subtle variations created microenvironments, each offering slightly different conditions that could support a range of organisms. What had once been a relatively uniform seafloor began to develop complexity in both form and function. As these reef structures expanded, they influenced the movement of water itself. Currents were redirected, broken into smaller flows that carried nutrients and oxygen through the intricate passages within the reef. This circulation supported a variety of feeding strategies, from organisms that filtered suspended particles to those that grazed along surfaces or scavenged within protected spaces. The reef did not merely host life, it actively shaped the conditions that allowed different forms to coexist. Within these environments, interactions grew more layered. Organisms occupied specific niches, their roles defined by both their anatomy and their position within the structure. Some remained attached, contributing to the reef's growth, while others moved across its surfaces or through its openings, forming early food webs that connected multiple levels of consumption and energy transfer. These relationships were not yet as intricate as those seen in later ecosystems, but they represented a clear shift toward organized ecological networks. The presence of such communities marked a transition in how life occupied the ocean. Instead of existing primarily as individuals dispersed across open space, organisms now clustered within shared habitats that offered both opportunity and constraint. The reef created boundaries and pathways, concentrating activity and shaping encounters in ways that influenced survival and reproduction. Through these early constructions, the sea began to resemble a landscape with defined features rather than a continuous expanse. The accumulation of skeletal material, the interaction of water with structure, and the gathering of diverse organisms all contributed to a new level of environmental complexity. In these quiet, slowly growing formations, the foundations of later marine ecosystems took shape, establishing patterns of community and interaction that would persist even as the specific builders and inhabitants continued to change. Along the shifting margins where sea met sediment, new shapes began to extend beyond the scale that had once defined these waters. Their presence marked not only by size, but by the way they interacted with both water and land. Eurypterids, often called sea scorpions, emerged as some of the largest arthropods of their time, their bodies lengthening into forms that could exceed 2 meters, carrying a weight and reach that set them apart within coastal environments. Their anatomy reflected a balance between strength and flexibility. Broad, segmented bodies tapered toward a tail that could assist in steering, while paired appendages extended from the underside, each specialized for a different function. Some limbs were adapted for walking along soft substrates, pressing into the sediment with controlled force, while others formed paddle-like structures that enabled short bursts of swimming. This dual capacity allowed eurypterids to move between shallow waters and the edges of exposed ground, occupying a transitional space that offered both opportunity and concealment. At the front, their appendages evolved into tools suited for capture. In certain forms, these limbs bore spines or grasping surfaces that could secure smaller organisms, drawing them inward with deliberate motion. Their sensory structures, though less elaborate than those of earlier visual specialists, provided sufficient awareness to detect movement and proximity, guiding their actions within environments where visibility could shift with changing water, clarity, and light. The coastal zones they inhabited were dynamic, shaped by tides, currents, and the gradual accumulation of sediment. These conditions created areas where water depth varied, forming channels, pools, and flats that could either expose or conceal depending on the moment. Eurypterids used this variability to their advantage, positioning themselves within shallow waters or partially buried in soft sediment, where their bodies blended with the surroundings. From these positions, they could remain still for extended periods, conserving energy while waiting for smaller organisms to pass within reach. Evidence of their movement remains etched into ancient surfaces, preserved as fossilized trackways that record the impression of limbs pressing into soft ground. These traces reveal patterns of motion that shift between steady walking and more irregular sequences, suggesting pauses, turns, and changes in direction. In some cases, the trackways extend from submerged areas onto what would have been exposed flats, indicating that certain eurypterids ventured briefly beyond the water, their bodies supported by their limbs as they crossed damp surfaces. Such records provide a quiet insight into behavior, capturing moments that unfolded long before more complex ecosystems developed. The presence of large arthropods in these environments added a new dimension to coastal life, introducing interactions that extended across both water and land. Their size alone altered the scale at which encounters occurred, while their ability to occupy multiple zones increased their influence within these early systems. As eurypterids moved through these margins, they contributed to a broader pattern of expansion, where organisms began to explore not just new forms, but new spaces. The boundaries between habitats became less defined, allowing life to extend its reach into areas that had previously remained unoccupied. Within this gradual widening of possibility, the coastal world grew more complex, shaped by creatures that carried both the memory of earlier forms and the beginnings of something that would continue to evolve beyond the sea. A quiet shift unfolded within certain lineages, one that did not immediately change the appearance of the ocean, yet would gradually reshape its balance. Structures that once served only to draw in water and filter particles began to harden and articulate, forming the earliest versions of jaws. This transformation allowed a new way of feeding, one that involved grasping rather than drifting intake, bringing precision and force into interactions that had previously been diffuse. With the emergence of jaws came a reorganization of the head. Cartilaginous supports strengthened, muscles attached in new patterns, and openings aligned to guide water flow while allowing controlled biting motions. These changes were not isolated, but part of a broader shift in how certain organisms engaged with their surroundings. Feeding became an active process, requiring coordination, timing, and the ability to seize and manipulate food directly. Among the early groups to embody these developments were the placoderms, a diverse collection of armored fishes whose bodies carried a combination of rigid protection and flexible movement. Their heads and upper bodies were encased in bony plates that formed a shield, while the rear portions remained more mobile, allowing them to swim with increasing efficiency. This contrast between stability and motion created a form that could both withstand pressure and navigate through water with control. Within this group, some species grew to considerable size, their presence defined by both mass and capability. Dunkleosteus stands as a notable example, its head enclosed in thick plates that joined at the front to form powerful jaw edges. Instead of teeth in the modern sense, these edges functioned as sharpened surfaces that could close with significant force, enabling it to process other armored organisms. The mechanics of its bite reflected a convergence of strength and design, where bone served both as protection and as a tool for feeding. As these fishes moved through their environment, their swimming patterns became more refined. Fins developed shapes that improved stability and propulsion, reducing drag and allowing for smoother, more directed motion. The ability to accelerate, turn, and maintain speed offered advantages in both capturing prey and avoiding threats. Movement itself became a defining trait, with certain species occupying open water rather than remaining close to the seafloor or within structured habitats. This shift in mobility altered the distribution of life within the ocean. Faster swimmers could traverse greater distances, accessing resources that were previously out of reach and interacting with a wider range of organisms. The water column became a space of activity, where encounters occurred not only through proximity, but through pursuit and evasion across open space. The presence of armored fishes introduced a new balance between protection and agility. While their bony plates provided defense, they also required adaptations in movement to offset added weight. The solutions that emerged varied, with some species favoring heavier protection and slower motion, while others reduced armor in favor of speed. These variations reflected different strategies within a shared framework, each one testing how best to survive within an increasingly dynamic environment. As jaws, armor, and refined movement combined, the ocean entered a phase where vertebrate life began to play a more prominent role. The patterns established during this time would continue to evolve, shaping the direction of marine ecosystems in ways that extended far beyond their initial appearance. Pressure gathered at the front of a moving body, not as speed alone, but as force waiting to be released in a single, controlled motion. Dunkleosteus carried this potential within its head, where thick bony plates met along sharpened edges, forming a mechanism that could close with remarkable power. Each movement of its jaws was guided by strong muscles anchored to reinforced structures, allowing the plates to snap together with a precision that turned bone into both weapon and tool. The edges of these plates were not fixed in a static shape. As they met and slid against one another, they maintained a sharpness through use, wearing in a way that preserved their effectiveness over time. This self-sharpening quality ensured that each closure remained efficient, capable of cutting or crushing depending on the resistance encountered. The design did not rely on replacement teeth, but on the interaction between surfaces that refined themselves through repeated motion. When Dunkleosteus moved through the water, its body balanced mass with control. The armored head provided protection and strength, while the rear of the body allowed for propulsion that could carry it forward with deliberate force. It did not require constant speed, but instead relied on well-timed acceleration, closing distance in moments that mattered. Its presence shaped the surrounding space, as other organisms adjusted their positions, their movements influenced by the possibility of sudden contact. Within its environment, Dunkleosteus occupied a position at the uppermost level of interaction, engaging with other large organisms and capable of overcoming defenses that had once provided security. The armored exteriors that had defined earlier success were no longer absolute barriers, as the force generated by its jaws could fracture or bypass them. This shift altered the balance between protection and vulnerability, introducing a new standard for what constituted effective defense. The rise of such fishes marked a gradual transition in dominance as vertebrate forms began to exert greater influence over marine ecosystems. Arthropods, once prominent across a range of habitats, encountered competitors that combined internal support structures with external armor and refined feeding mechanisms. The integration of these features allowed for a different kind of adaptability, one that supported both strength and sustained movement. As this change unfolded, the interactions within the ocean became increasingly shaped by vertebrate capabilities. Feeding strategies evolved in response, with organisms adapting either to evade, withstand, or coexist with these new pressures. The presence of Dunkleosteus exemplified this shift, not as an isolated case, but as part of a broader pattern in which certain traits aligned to create forms that could dominate their surroundings. The influence of such predators extended beyond individual encounters, contributing to the restructuring of ecological relationships across wide areas. Their ability to process a variety of prey types allowed them to occupy central roles within food webs, linking different levels of the ecosystem through their actions. In doing so, they helped define a new phase in marine life, where the combination of internal skeletons, external armor, and powerful jaws set the foundation for future developments. Through this convergence of features, the ocean moved further from its earlier configurations, carrying forward the changes that had begun with simpler interactions into a state where force, structure, and movement worked together to shape the course of life beneath the surface. The sea no longer functioned as a single, continuous space, but began to separate into layers that differed in light, pressure, and activity, each one supporting its own patterns of life. Near the surface, where sunlight still filtered through, microscopic organisms multiplied in new forms, drifting in vast numbers that shifted with currents and seasons. These planktonic communities became more varied, their shapes and compositions changing in ways that allowed them to occupy slightly different positions within the water, capturing light or nutrients with increasing efficiency. This diversification at the smallest scale carried broader consequences. As plankton expanded in variety and abundance, they provided a more stable and continuous source of energy for larger organisms. Feeding strategies adjusted to take advantage of these changes, with some species developing fine structures suited for filtering suspended particles, while others adapted to consume those filter feeders in turn. The flow of energy began to organize into chains and networks, connecting multiple levels of life in ways that extended beyond direct contact. Beneath the surface layers, deeper regions of the ocean became more active. Organisms moved into waters where light diminished and conditions shifted, exploring spaces that had previously remained less occupied. These deeper zones required different adaptations as visibility decreased and pressure increased, shaping bodies and behaviors that could function under such constraints. Movement patterns altered, feeding methods diversified, and interactions became less dependent on sight, relying instead on other forms of perception. As these vertical divisions became more defined, ecological niches emerged with greater clarity. Each layer, from the illuminated surface to the dimmer depths, offered distinct opportunities and limitations. Organisms began to specialize, aligning their structures and behaviors with the specific conditions of their chosen environments. Some remained near the surface, where energy was more readily available, while others occupied intermediate depths, navigating between zones, and still others settled into deeper waters, where resources were less abundant, but competition could be reduced. This specialization extended across the seafloor as well, where variations in sediment, depth, and water movement created localized habitats that supported different communities. Certain organisms thrived in areas with steady currents that brought a continuous supply of particles, while others adapted to calmer regions where finer materials accumulated. The ocean floor, once relatively uniform in its function, developed a patchwork of environments, each contributing to the overall complexity of the system. Interactions within these expanding networks became more intricate. Predators, grazers, filter feeders, and scavengers formed interconnected relationships where changes at one level could influence others in subtle ways. The presence of multiple pathways for energy flow provided a degree of stability, allowing ecosystems to persist even as individual species rose or declined. Through these layered structures and specialized roles, the ocean evolved into a system defined by connection and variation. Life no longer spread evenly across a simple expanse, but arranged itself within a framework that balanced distribution and concentration, movement and stillness. In this growing complexity, the sea continued to shape and be shaped by the organisms within it, each adaptation contributing to a broader pattern that would support further change. Invisible shifts began to alter the rhythm of life, not through form or movement at first, but through the composition of the water itself. Dissolved gases accumulated gradually, carried through cycles of production and exchange that unfolded over vast spans of time. Among these changes, oxygen reached levels that allowed organisms to access greater amounts of energy, not by introducing something entirely new, but by amplifying processes that had already begun to take shape. As oxygen became more available, metabolic pathways could operate with increased efficiency, supporting activity that required sustained energy output. Cells processed nutrients more rapidly, tissues maintained function over longer periods, and movement could be extended without immediate exhaustion. This did not create instant transformation, but it expanded the limits within which life could operate, offering new possibilities for growth, repair, and motion. In marine environments, these changes influenced the scale at which organisms could exist. Larger bodies require more energy to maintain, and the availability of oxygen played a role in determining how far size could increase without compromising function. As conditions allowed for greater metabolic support, certain lineages expanded in form, their structures accommodating increased mass while retaining coordination and balance. The relationship between size and energy became more flexible, allowing organisms to explore dimensions that had previously been constrained. At the same time, the distribution of oxygen within the ocean was not uniform. Surface waters, influenced by contact with the atmosphere and the activity of photosynthetic organisms, often contained higher concentrations, while deeper regions could remain comparatively limited. This gradient shaped where certain organisms could thrive, guiding movement and settlement across different depths. Species adapted to these variations, developing physiological traits that aligned with the oxygen levels of their preferred habitats. The influence of oxygen extended beyond individual organisms, affecting entire ecosystems through its role in chemical processes. The breakdown of organic material, the cycling of nutrients, and the interactions between water and sediment all depended, in part, on the availability of this element. As oxygen levels shifted, these processes adjusted, altering the conditions under which life persisted and interacted. During intervals such as the Carboniferous, when oxygen concentrations rose more significantly, the effects became more pronounced. Increased availability supported not only larger forms, but also higher levels of activity, influencing feeding, movement, and reproduction. These changes did not act in isolation, but interacted with other factors such as temperature, nutrient supply, and competition, creating a complex web of influences that shaped the direction of evolution. Through these gradual adjustments, the chemistry of the ocean revealed its role as a quiet architect, guiding biological possibilities without direct visibility. The forms that emerged, the behaviors that developed, and the relationships that formed were all influenced by conditions that could not be seen, yet were constantly present. In this interplay between chemistry and life, the boundaries of what organisms could become continued to expand, shaped by elements that moved silently through the water, sustaining and transforming the world beneath the surface. From the ocean floor rose forms that did not swim or crawl, but stood upright in slow, deliberate stillness, extending themselves into the water like living structures shaped by both biology and current. Crinoids, distant relatives of starfish, anchored themselves by slender stalks that attached firmly to the substrate, lifting their bodies upward into the moving water above. At their upper ends, feathery arms spread outward in delicate arrays, forming intricate patterns that shifted gently with the flow. These arms were lined with fine structures designed to capture particles suspended in the water, drawing them inward through coordinated motion. Each movement was subtle, almost imperceptible, yet continuous, creating a steady intake of organic material. In dense groupings, crinoids covered wide stretches of the seafloor, their stalks forming a vertical layer that transformed the space into something more structured, more enclosed, as if the ocean had grown a quiet forest beneath its surface. Within these formations, water moved differently. Currents slowed and divided as they passed through the array of arms, creating zones where particles lingered longer before being carried away. This altered flow supported a range of smaller organisms that lived among the crinoids, taking advantage of the shelter and the steady supply of food. The seafloor, once more open and uniform, became a place of variation, where vertical structures introduced depth and layering into the habitat. The crinoids themselves remained largely stationary, their survival dependent on the consistency of the surrounding water rather than active movement. Their bodies reflected a balance between fragility and persistence, with skeletal elements providing support while allowing flexibility in response to shifting currents. When disturbed, some could adjust their posture slightly, folding or reorienting their arms, but their existence was defined more by placement than by motion. Around and within these living structures, other organisms adapted to the conditions they created. Some settled on the stalks, attaching themselves in positions where food particles were more likely to pass. Others moved slowly across the seafloor beneath, navigating the shaded spaces between the stems. Predatory forms entered these environments as well, their movements influenced by the density and arrangement of the crinoids, using the structure as both obstacle and cover. The overall effect was one of quiet complexity. The constant filtering activity of the crinoids linked the water column to the seafloor, transferring energy downward in a steady flow. This connection supported a network of interactions that extended beyond any single organism, shaping a community that relied on both stability and subtle variation. Visually, these environments carried an unfamiliar character. The upright forms, the gentle motion of countless arms, and the layered arrangement of life created a landscape that differed from open water or flat seabeds. It was calm, yet structured in ways that felt distinct from later marine ecosystems, reflecting a stage in which life explored vertical space without the need for speed or constant movement. Within these underwater forests, the ocean expressed another mode of organization, one built not on pursuit or evasion, but on position and flow. The presence of crinoids demonstrated how life could shape its surroundings through stillness, creating environments that supported diversity through quiet, continuous interaction. Movement began to favor fluidity over weight, as certain forms shed the heaviness of mineralized armor and replaced it with structures that bent rather than resisted. Among these were the early cartilaginous fishes, ancestors of sharks, whose internal frameworks were composed not of dense bone, but of lighter, more flexible material. This change did not reduce their strength, but redistributed it, allowing their bodies to absorb force and maintain motion with less resistance. Their skeletons, built from cartilage, provided a balance between support and adaptability. Instead of rigid joints and plates, their bodies could curve smoothly, transferring energy along their length as they swam. Each motion flowed into the next, creating a continuous wave that propelled them forward with efficiency. This flexibility allowed for sudden adjustments in direction, enabling precise navigation through the water, where small changes in angle could determine the success of an approach or the avoidance of contact. The shape of their bodies reflected this emphasis on movement. Streamlined forms reduced drag, while fins positioned along their sides and back provided stability and control. The tail, often asymmetrical, generated thrust in a way that maintained forward momentum without excessive effort. These features combined to create swimmers that could sustain motion over longer distances, covering space in ways that heavier organisms could not easily match. Beyond their physical structure, their sensory systems introduced another level of interaction with the environment. Their eyes, adapted to varying light conditions, allowed them to detect movement and contrast even in dimmer waters. More subtle still were the systems that responded to vibrations and electrical signals, enabling them to perceive disturbances generated by other organisms. These senses extended their awareness beyond what was visible, allowing them to detect presence through the faintest shifts in the surrounding medium. Feeding strategies aligned with these capabilities. Rather than relying solely on strength or sudden force, these fishes used a combination of speed, perception, and timing. They could approach from angles that reduced detection, adjust their movement in response to subtle cues, and close distance with controlled acceleration. Their jaws, equipped with rows of replaceable teeth, provided a means of grasping and processing a variety of prey types, maintaining effectiveness even as individual teeth wore down or were lost. As these cartilaginous fishes moved through the ocean, they occupied roles that emphasized efficiency over sheer power. Their presence introduced a different style of predation, one that relied on continuous motion and refined sensing rather than heavy armor or singular force. This approach allowed them to interact with a wide range of organisms, adapting their behavior to different conditions and opportunities. The emergence of these forms contributed to a broader diversification of vertebrate life, adding new strategies to the evolving network of interactions within the sea. Their flexible bodies, advanced sensory systems, and efficient movement patterns established a foundation that would persist through later periods, shaping the development of marine predators in ways that extended far beyond their initial appearance. A gradual cooling began far from the water, high across ancient landmasses, where ice slowly gathered and expanded, altering the balance between ocean and atmosphere in ways that unfolded with quiet persistence. As temperatures shifted, vast quantities of water became locked within growing ice sheets, reducing the volume of the seas and exposing areas that had long remained submerged. Shorelines retreated, and the shallow marine environments that had supported diverse communities began to shrink. These shallow regions had served as centers of activity where light, nutrients, and stable conditions allowed a wide range of organisms to thrive. As sea levels fell, many of these habitats disappeared, replaced by exposed sediment, or transformed into environments that no longer supported the same forms of life. The intricate structures built over long periods, including reef systems and seafloor communities, were disrupted as the conditions they depended on changed beyond their capacity to adapt. The cooling of the ocean itself introduced further challenges. Temperature influences the solubility of gases, the rate of chemical reactions, and the physiology of organisms, and even gradual changes can alter the balance within ecosystems. As waters cooled, metabolic processes slowed, affecting growth, reproduction, and the ability to respond to environmental stress. Species that had evolved under more stable conditions found themselves constrained by shifts that extended across entire regions. The combination of shrinking habitats and changing conditions created a cascade of effects. Organisms that relied on specific environments lost access to the spaces they needed, while others faced new forms of competition as remaining habitats became more crowded. Food webs, once supported by a steady flow of energy through established pathways, began to fragment as key species declined or disappeared. Each loss carried consequences for other organisms, amplifying the overall impact. In the fossil record, this period is marked by a noticeable reduction in diversity, as many lineages that had flourished earlier in the Paleozoic vanish from the layers of sediment. Trilobites, brachiopods, and other groups that had occupied prominent roles experienced significant declines. Their presence diminished across wide areas. The absence of these forms in subsequent layers reflects not a sudden disappearance in a single moment, but a prolonged interval of stress and reduction. Despite the scale of these changes, the process unfolded without abrupt transitions visible within any single location. Instead, it appeared as a gradual thinning of life, a quiet contraction of diversity that extended across different environments. Some regions retained pockets of stability, where certain species persisted, while others became increasingly sparse. The ocean, once filled with varied and interconnected communities, entered a phase where simplicity began to replace complexity. The interactions that had defined earlier systems were reduced, leaving behind more limited networks that could function under altered conditions. This contraction did not erase life entirely, but it reshaped the composition of marine ecosystems, setting the stage for new forms to emerge in the spaces left behind. Within this cooling world, the balance between environment and organism shifted toward constraint, demonstrating how changes beyond the immediate reach of the ocean could influence life beneath its surface. After the long contraction, life did not return in the same arrangement it had lost, but reassembled itself through pathways that favored flexibility and speed of adaptation. In the spaces left behind, surviving lineages expanded into roles that had once been occupied by others, reshaping interactions in ways that reflected both memory and change. The ocean did not restore its previous balance. It composed a new one from the fragments that remained. Repopulation began unevenly, with certain groups recovering more quickly than others. Organisms capable of tolerating a wider range of conditions spread across available habitats, their resilience allowing them to establish presence where more specialized forms could not. This early stage of recovery was marked by simplicity, with fewer competing strategies and more open ecological space, allowing populations to grow without the constraints that had once limited them. As these communities expanded, variation reemerged. Small differences in structure or behavior became opportunities, leading to diversification as lineages adapted to specific conditions. Feeding strategies began to diverge, with some organisms refining methods of capturing suspended particles, while others developed ways to consume mobile prey or scavenge organic material. These distinctions created layers within the ecosystem, gradually rebuilding the networks that had been reduced. Predatory relationships returned with renewed intensity, though their structure differed from earlier configurations. New hierarchies formed, shaped by the traits that proved effective under changing conditions. Organisms that combined efficient movement with adaptable feeding mechanisms gained influence, occupying positions that allowed them to interact with multiple levels of the food web. These predators were not exact replacements for those that had disappeared, but they fulfilled similar roles through different means. Along the seafloor, construction resumed in a quieter form. Reef systems began to rebuild, not as immediate recreations of previous structures, but as evolving frameworks shaped by the organisms available at the time. Early reef builders established new foundations, their skeletal remains accumulating to form structures that supported additional life. These formations grew gradually, influenced by water movement, sediment, and the interactions of the organisms within them. The return of these structures introduced complexity once again, creating environments where multiple species could coexist within shared spaces. As reefs expanded, they provided surfaces for attachment, shelter from currents, and areas where food could concentrate. This allowed for the development of more intricate communities, where interactions extended across different levels and roles. Throughout this process, the pace of change remained steady rather than abrupt. Evolution proceeded through accumulation, with each generation contributing slight adjustments that, over time, resulted in significant transformation. The ocean systems grew more interconnected, though not identical to their earlier forms, reflecting a history that had been altered by loss. The recovery demonstrated that life could reorganize under new conditions, finding pathways that supported continued existence even after substantial disruption. The patterns that emerged carried traces of what had come before, yet they also introduced new directions, setting the stage for further developments as the ocean continued to evolve. At the margins, where water thinned and the seafloor rose closer to the surface, certain fishes began to move differently, not faster or more forcefully, but with a kind of contact that linked their bodies to the ground beneath them. These were the lobe-finned fishes, whose paired fins extended from the body on fleshy bases, supported by internal structures that resembled the earliest outlines of limbs. Instead of acting only as stabilizers or steering surfaces, these fins could press against the substrate, shifting weight and adjusting position with a degree of control that had not been present in earlier forms. Within these fins, bones arranged in simple sequences provided a framework that allowed movement in multiple directions. Muscles attached along these elements enabled subtle rotations and pushes, giving the fish the ability to navigate uneven surfaces in shallow environments. This was not yet walking in the sense that would later define terrestrial animals, but it introduced a way of interacting with solid ground that went beyond swimming alone. The environments these fishes occupied were often variable and unpredictable. Shallow waters could warm quickly, lose oxygen, or recede as conditions changed, creating temporary pools and channels separated by exposed sediment. In such settings, the ability to move along the bottom or between isolated pockets of water offered a clear advantage. Lobe-finned fishes could brace themselves, push forward in short movements, and maintain position in areas where currents shifted or space became limited. Their bodies reflected these demands. Alongside their distinctive fins, Some developed lungs or lung-like structures, allowing them to supplement oxygen intake when water conditions were less favorable. This adaptation did not replace gill function, but added another layer of flexibility, enabling survival in environments where oxygen levels fluctuated. The combination of supportive fins and alternative breathing methods allowed these fishes to occupy ecological spaces that others could not easily access. As these capabilities emerged, the boundary between water and land became less absolute. The transition was not a sudden crossing, but a gradual extension of behavior into zones where water depth varied and contact with air was more frequent. Movement across damp surfaces, brief exposure to the atmosphere, and the use of fins for support all contributed to a slow expansion of possibilities. These shallow environments acted as testing grounds where small changes in structure and function could produce noticeable effects on survival. Organisms that could navigate both water and substrate, that could tolerate shifts in oxygen availability, and that could adjust to changing conditions gained opportunities to persist and spread. Over time, these incremental advantages accumulated, shaping lineages that would continue to develop along these pathways. The emergence of limb-like fins did not immediately lead to life on land, but it established the foundation upon which such a transition could occur. By linking movement to contact with the ground and expanding the ways in which oxygen could be obtained, lobe-finned fishes introduced a new relationship between organism and environment. Within the quiet, shifting margins of the sea, the first steps toward a different world began to take form, not through abrupt change, but through steady adaptation to conditions that invited exploration beyond the water's edge. Far from the shifting margins and structured seafloors, the open water began to take on a character of its own, expanding into a vast interior where movement unfolded across depth as much as distance. Within this broad space, certain forms adapted to a life suspended between surface and seafloor, navigating layers that differed in light, pressure, and resource availability. Among the most prominent of these were the nautiloids, whose elongated or coiled shells carried internal chambers that allowed precise control over buoyancy. These chambers, connected by a narrow tube, could be adjusted by regulating gases and fluids, enabling the organism to rise or sink with minimal effort. This capacity did not produce rapid motion, but it allowed a measured ascent or descent through the water column, aligning position with changing conditions. The shell itself provided protection while also serving as a stabilizing structure, guiding orientation as the animal moved through different depths. Nautiloids used this control to occupy regions where food could be accessed at different times, participating in patterns of vertical movement that followed the distribution of smaller organisms. As light faded with depth, certain prey gathered in layers, shifting upward or downward depending on environmental cues. By adjusting their position, nautiloids could intersect these movements, maintaining access to resources without remaining confined to a single zone. The ocean, in turn, became more distinctly layered. Differences in temperature, salinity, and density created boundaries that influenced how water mixed and how nutrients were distributed. These layers were not rigid divisions, but gradients that shaped the movement of organisms and the availability of energy. Life began to organize itself within these vertical structures, with species adapting to the specific conditions found at different depths. In the upper layers, where light remained present, activities centered around organisms that depended on photosynthetic processes or the abundance of plankton. Below, in dimmer regions, other forms adapted to reduced visibility, relying on alternative sensory mechanisms and slower movement patterns. The deeper waters, more stable but less productive, supported organisms that could persist with limited resources, their interactions unfolding at a different pace. Nautiloids moved among these layers with a steadiness that reflected their design. Their propulsion, driven by expelling water through a siphon, allowed controlled forward motion, while buoyancy adjustments provided vertical positioning. This combination enabled them to explore a range of depths, linking different parts of the ocean through their movement and feeding behavior. The expansion of life into these open waters added another dimension to marine ecosystems. Interactions were no longer confined to surfaces or immediate surroundings, but extended across vertical space, connecting layers that differed in both conditions and inhabitants. This complexity increased the pathways through which energy and nutrients could flow, supporting a broader range of strategies and adaptations. Through these developments, the ocean continued to diversify, not only in the forms of life it contained, but in the ways those forms occupied space. The presence of organisms capable of navigating depth as well as distance contributed to a more integrated system, where the structure of the water itself became a defining element in the organization of life. Motion began to favor those who could reduce resistance, shaping bodies that slipped through the water with less effort and greater control. Forms that once carried broader outlines or heavier structures gradually refined into narrower profiles, their surfaces smoothing, their proportions aligning with the flow around them. This change did not occur in isolation, but as a response to increasing interaction, where encounters depended not only on presence, but on the ability to close distance or create it. As competition intensified, even small differences in movement carried significance. Organisms that could accelerate more quickly, adjust direction with precision, or maintain speed over longer distances gained access to resources that others could not reach as efficiently. These advantages influenced survival in subtle ways, guiding the gradual reshaping of bodies across multiple lineages. Streamlining became a shared solution, appearing in varied forms as different groups converged on similar principles of movement. Fins, once simple extensions used primarily for stability, evolved into structures capable of fine control. Their placement along the body, their shape, and their flexibility all contributed to how motion was generated and maintained. Paired fins allowed for adjustments in pitch and direction, while median fins provided balance and reduced unwanted rotation. The tail, acting as the primary source of propulsion, developed forms that transferred energy more effectively, converting muscular movement into forward motion with greater efficiency. These refinements allowed organisms to navigate increasingly dynamic environments. Open water demanded sustained movement, while structured habitats required careful maneuvering through confined spaces. The ability to shift between these modes of motion expanded the range of conditions in which a species could operate. Movement became not just a means of travel, but a central element of interaction, influencing feeding, avoidance, and positioning within the ecosystem. The pressure to move efficiently also affected behavior. Patterns of pursuit and evasion became more intricate, with organisms adjusting their timing and trajectory in response to others. Encounters unfolded over shorter intervals, as speed reduced the time between detection and contact. This compression of interaction favored those capable of responding quickly, both in physical movement and in the coordination of sensory input with action. As these dynamics developed, the ocean supported a broader range of movement strategies, from steady cruising to rapid bursts of acceleration. Each approach reflected a balance between energy use and effectiveness, shaped by the conditions in which it was employed. Some species favored endurance, maintaining consistent motion across distances, while others relied on sudden changes in speed to capture or escape. The cumulative effect of these changes was a system in which agility became as important as strength. The ability to move through water with precision and efficiency influenced access to food, avoidance of threats, and the capacity to explore new areas. Over time, these pressures reinforced the importance of streamlined forms and refined fins, embedding them within the broader pattern of marine evolution. Within this shifting balance, motion itself became a defining feature of life beneath the surface, guiding how organisms interacted with one another and with the space they occupied. As the ocean continued to shape and be shaped by the forms moving through it, change returned not as a single disturbance, but as a series of shifts that unfolded across time, each one altering the balance just enough to weaken what had been rebuilt. The structures that had quietly expanded along the seafloor began to falter, their growth interrupted by conditions that no longer supported their stability. Reef systems, once steady frameworks of accumulation and interaction, started to decline, their layered forms breaking down as the organisms that maintained them struggled to persist. The causes lay partly within the chemistry of the ocean, where oxygen levels began to fluctuate in ways that reduced its availability in certain regions. As oxygen diminished, especially in deeper or more isolated waters, organisms that depended on steady supply found themselves constrained. Metabolic processes slowed, movement became less sustainable, and the capacity to recover from stress weakened. These effects did not occur uniformly, but appeared in patches, creating zones where life thinned or disappeared entirely. The decline of reefs had consequences that extended beyond their immediate presence. These structures had supported diverse communities, providing surfaces for attachment, shelter from currents, and a steady flow of resources. As they weakened, the habitats they created also vanished, leaving organisms without the conditions they required. The loss of these environments reduced the complexity of local ecosystems, simplifying interactions and limiting the range of species that could remain. At the same time, the changes in oxygen influenced broader patterns within the ocean. Water layers that had once supported active exchange became more stratified, restricting the movement of nutrients and gases between depths. This separation intensified the effects of depletion as areas with low oxygen became more isolated, making recovery more difficult. Organisms adapted to specific conditions faced new constraints, with fewer pathways available for adjustment. The impact of these changes did not occur in a single moment, but through a series of extinction pulses that extended across a prolonged interval. Each phase reduced diversity further, removing species that could not adapt to the shifting conditions. Between these pulses, partial recoveries occurred, with some organisms expanding into available spaces, only to face additional stress as conditions changed again. This pattern of decline and temporary stabilization created a drawn-out process that reshaped marine life gradually. Fossil records from this period reflect these fluctuations, showing intervals where diversity decreases, followed by brief increases, then further reductions. The repeated nature of these changes suggests a system under ongoing stress, where no stable equilibrium could be maintained for long. The ocean did not collapse entirely, but it lost many of the forms and structures that had defined its earlier complexity. Through this extended crisis, ecosystems became more simplified, with fewer species occupying broader roles. The intricate networks that had developed were reduced, leaving behind communities that could function under constrained conditions. The effects of this period carried forward, influencing which lineages would persist and which would fade from the record. Within this gradual unraveling, the ocean demonstrated how sustained environmental change could reshape life over time, not through a single event, but through a sequence of pressures that steadily altered the possibilities for survival and growth. Stability returned, not as a restoration of what had been lost, but as a quieter rebalancing, where surviving lineages settled into roles shaped by the conditions that remained. The ocean, having passed through extended periods of disruption, began to support more consistent patterns once again, though these patterns reflected a different arrangement of life. In this renewed equilibrium, certain groups expanded, their traits aligning with the demands of a system that favored flexibility and efficiency. Among these were the sharks, whose earlier forms had already demonstrated the advantages of streamlined movement and refined sensory perception. As conditions steadied, their diversity increased, with lineages branching into a range of shapes and behaviors suited to different environments. Some remained in open water, moving across wider areas, while others adapted to more confined spaces, adjusting their bodies and strategies to match the structure of their surroundings. This diversification allowed them to occupy multiple levels within the ecosystem, interacting with both smaller organisms and larger competitors. Alongside them, ammonoids rose to prominence, their coiled shells marking a lineage that balanced protection with buoyancy control. These organisms refined their ability to regulate position within the water, adjusting their depth with subtle changes that allowed them to access resources across different layers. Their shells, often more tightly coiled and varied in ornamentation, reflected a diversification that paralleled that of other groups, each form adapting to specific conditions within the ocean's vertical structure. The interactions between predators and prey became more intricate as these groups expanded. No longer defined by a few dominant forms, the ecosystem supported a network of relationships where multiple species influenced one another simultaneously. Predators developed strategies that combined movement, perception, and timing, while prey adapted through changes in behavior, structure, or distribution. These interactions unfolded continuously, shaping the dynamics of the system in ways that balanced opportunity with constraint. Food webs regained complexity, with energy flowing through multiple pathways that connected different organisms across various depths and habitats. Filter feeders, grazers, active hunters, and scavengers all contributed to a network that could sustain itself even as individual species fluctuated in abundance. This interconnectedness provided a degree of resilience, allowing the system to absorb changes without immediate collapse. The ocean floor and open water alike reflected this renewed organization. Habitats supported a range of specialized roles, each contributing to the overall function of the ecosystem. Organisms adapted to particular niches, refining their structures and behaviors in response to both environmental conditions and interactions with other species. This specialization created a balance where diversity and stability coexisted, each reinforcing the other. As these patterns settled into place, the ocean entered a phase where complexity could be maintained over longer intervals. The lessons of earlier disruptions remained embedded within the system, influencing which traits persisted and which did not. Through this gradual stabilization, marine life continued to evolve, building upon the foundations that had survived and shaping a world where interaction, adaptation, and continuity moved together in a steady, enduring flow. Continents that had once been scattered began to draw together, their slow movement across the planet's surface converging into a single, immense landmass. As these pieces joined, they formed Pangaea, a supercontinent that altered the shape of the oceans around it, compressing some regions while expanding others. The surrounding waters reorganized into a vast superocean, its boundaries defined by the edges of this unified land. Along the margins of Pangaea, extensive, shallow seas developed, spreading across low-lying areas where the land met the water. These regions were broad and relatively warm, receiving sunlight that penetrated easily through their depth, supporting a range of marine life adapted to such conditions. The seafloor in these areas provided space for communities to establish themselves, while the gentle slopes of the continental shelf created gradual transitions between land and deeper water. The configuration of the supercontinent influenced circulation patterns within the ocean. Currents moved differently along the extended coastlines, redistributing heat and nutrients in ways that shaped local environments. In some areas, water remained relatively stable, while in others, movement carried resources across wide distances, linking regions that might otherwise have remained isolated. These patterns contributed to the distribution of life, guiding where certain organisms could thrive. Global temperatures during this time remained elevated, creating conditions that supported widespread marine activity in shallow regions. Warm waters can hold less dissolved oxygen than cooler ones, yet the overall system balanced these effects through circulation and biological processes. Organisms adapted to these conditions, their structures and behaviors reflecting an environment where temperature played a significant role in shaping metabolism and interaction. Within these shallow seas, ecosystems expanded, drawing upon the stability provided by consistent warmth and available space. Reefs and other seafloor communities developed in areas where conditions allowed, while open water supported organisms that moved across larger distances. The combination of broad habitats and interconnected systems allowed for diversity to increase, even as the underlying conditions imposed certain constraints. Further from the continental margins, deeper parts of the superocean extended across vast distances, their conditions influenced by the same global factors but expressed differently with depth. The contrast between shallow and deep environments created a range of ecological zones, each supporting distinct forms of life adapted to their specific conditions. These variations contributed to the overall complexity of the marine world during this period. The formation of Pangaea and its surrounding ocean reshaped not only geography, but also the relationships between organisms and their environments. The arrangement of land and water influenced climate, circulation, and the distribution of habitats, all of which played a role in guiding the direction of evolution. As these systems settled into place, the ocean entered a phase defined by both expansion and constraint, where large-scale structure influenced local experience. Within this superocean, life continued to adapt, filling the spaces created by shifting coastlines and evolving conditions. The patterns established during this time would carry forward, influencing the resilience and vulnerability of marine ecosystems as further changes approached. Subtle changes in the air above began to seep into the water below, carried through exchanges that never paused, slowly altering the composition of the sea in ways that were not immediately visible. Carbon dioxide accumulated in the atmosphere, and as it dissolved into the ocean, it shifted the balance of dissolved compounds, increasing acidity across wide regions. This transformation did not reshape the surface or the movement of water, but it changed the chemical environment that supported life at its most fundamental level. As acidity increased, organisms that depended on stable carbonate chemistry faced growing difficulty. The formation of shells and skeletal structures, processes that relied on the availability of carbonate ions, became less efficient. Structures that once formed with relative ease required more energy to maintain, and in some cases began to weaken or dissolve. The protective layers that had defined many lineages were no longer as reliable, altering both survival and interaction. At the same time, oxygen levels within the ocean declined in certain regions, influenced by a combination of factors that included temperature, circulation, and biological activity. Warmer waters, already holding less dissolved oxygen, further reduced its availability, while changes in circulation limited the replenishment of deeper layers. These conditions created zones where oxygen became scarce, restricting the types of organisms that could persist. In such environments, metabolic processes slowed or failed, affecting movement, feeding, and reproduction. Organisms that required consistent oxygen levels faced increasing stress, while those capable of tolerating lower concentrations gained relative advantage. This imbalance shifted the composition of communities, favoring forms that could endure conditions that others could not. The combination of acidification and oxygen depletion created a compounding effect. As some organisms declined, the structures they maintained, including reefs and other complex habitats, also weakened. The loss of these systems reduced the diversity of environments available, simplifying ecosystems and limiting the interactions that had previously supported stability. Evidence of these changes remains preserved within layers of sediment, where chemical signatures record variations in carbon and oxygen over time. These records reveal patterns of fluctuation, indicating periods when conditions shifted toward greater acidity and reduced oxygen. The consistency of these signals across different regions suggests a widespread transformation, not confined to isolated areas, but affecting the ocean as a whole. Within this altered chemistry, life continued, but under increasing constraint. The processes that had once supported growth and diversification now imposed limits, narrowing the range of viable forms. Adaptation remained possible, but it required adjustments that could not be achieved by all lineages. The ocean, shaped not only by movement and structure but by the composition of its own waters, entered a phase where invisible forces guided visible outcomes. Through these changes, the balance between organism and environment shifted once more, demonstrating how deeply life depends on conditions that operate beyond immediate perception, yet influence every interaction beneath the surface. Far to the north of the supercontinent, the ground itself began to open, releasing immense volumes of molten rock that spread across the surface in repeated outpourings. These eruptions, known as the Siberian traps, did not occur as a single event, but as a prolonged series of flows that covered vast regions with layers of basalt. With each pulse, gases were released into the atmosphere, altering its composition and setting in motion changes that would extend into the ocean. Among these gases, carbon dioxide increased significantly, strengthening the warming already present and pushing temperatures higher. As heat accumulated, the balance between ocean and atmosphere shifted, with warmer waters reducing the capacity to hold dissolved oxygen. At the same time, other compounds entered the system, contributing to chemical changes that affected both air and sea. The scale of these emissions was such that their influence reached across the planet, reshaping conditions over a relatively short span in geological terms. As warming intensified, additional sources of carbon were released from within the Earth's systems. Methane, stored in frozen deposits beneath the ocean floor and within sediments, began to escape as temperatures rose. This gas, more effective at trapping heat, accelerated the warming process further, creating a feedback loop that amplified the initial changes. The combined effect of volcanic emissions and methane release drove the environment toward conditions that had not been experienced for long periods. Within the ocean, these changes manifested as increasing stress across multiple levels. Elevated temperatures influenced metabolic processes, while reduced oxygen limited the ability of organisms to sustain activity. Acidification, already present, intensified as more carbon dioxide dissolved into the water, affecting the formation and maintenance of shells and skeletal structures. These factors did not act independently, but combined to create conditions that were difficult for many forms of life to endure. The impact on marine ecosystems unfolded rapidly. Species that had persisted through earlier fluctuations found themselves unable to adapt to the combined pressures of heat, chemical change, and oxygen depletion. Populations declined across wide areas, with entire groups disappearing from the fossil record within relatively short intervals. The networks that had supported complex interactions began to unravel as key species were lost, disrupting the balance that had maintained stability. As these losses accumulated, the ocean entered a phase where collapse became more widespread. Habitats that had supported diverse communities became increasingly sparse, with fewer organisms occupying broader roles. The reduction in biodiversity limited the pathways through which energy could flow, further weakening the system and reducing its capacity to recover. Sediment layers from this time preserve evidence of these changes, recording shifts in chemical composition that correspond to the environmental transformations taking place. These records reveal a convergence of factors that together drove one of the most extensive reductions in marine life, marking a turning point in the history of the ocean. Through this sequence of events, the connection between geological activity and biological outcome became clear, as processes originating deep within the earth reshaped the conditions at its surface, altering the course of life within the sea. Loss did not arrive as a single silence, but as a thinning that spread across the ocean until absence itself became the most common condition. Species that had once filled every layer, every niche, began to vanish in numbers so extensive that the structure of the ecosystem could no longer hold. This interval, the most severe reduction in life the planet has known, removed the vast majority of marine species, leaving behind only fragments of what had once been a complex and interconnected world. Reef systems, which had risen and fallen through earlier changes, now disappeared almost entirely. The organisms that built and maintained these structures could not withstand the combined pressures of warming, acidification, and reduced oxygen. Without them, the frameworks that had supported diverse communities dissolved, leaving seafloors more exposed and uniform. The intricate habitats that had once concentrated life into layered environments were replaced by simpler landscapes, where fewer organisms could find suitable conditions. At higher levels of interaction, the disappearance of apex predators marked a further unraveling. Creatures that had occupied dominant positions within the ecosystem, shaping the behavior and distribution of other species, were lost along with the systems that supported them. Their absence removed a key element of balance, altering how remaining organisms interacted and how energy moved through the ocean. Without these predators, the patterns of regulation that had once structured communities no longer applied. The collapse extended through every level of the food web. Primary producers declined in some regions, while consumers at various stages lost the resources they depended on. The connections that had linked organisms into stable networks began to break apart, each loss weakening the system further. As species disappeared, the pathways through which energy flowed became fewer and more fragile, reducing the resilience of the remaining communities. In the sedimentary record, this event is marked by a stark reduction in diversity, where layers that once contained a wide array of forms give way to intervals dominated by far fewer species. This shift reflects not only the disappearance of individual organisms, but the loss of entire lineages that had persisted for long periods. The continuity of life was interrupted on a scale that reshaped the direction of evolution. What remained were organisms capable of enduring conditions that had become hostile to many others. These survivors often shared traits of flexibility, tolerance, or simplicity, allowing them to persist where more specialized forms could not. Their presence did not restore the previous complexity, but established a foundation upon which new systems could eventually develop. The ocean, once characterized by abundance and variation, entered a phase where emptiness defined much of its space. Interactions became limited, habitats less structured, and diversity greatly reduced. Yet within this diminished world, the processes of life continued, setting the stage for gradual recovery. The magnitude of loss left a lasting imprint, influencing which forms would emerge and how future ecosystems would be shaped by the memory of what had been removed. Time passed with little to record, as if the ocean itself had entered a pause where the usual signatures of life grew faint within the layers of sediment. The rock that formed during this interval holds fewer traces, fewer impressions of shells or structured bodies, leaving behind stretches where absence becomes the most noticeable feature. These gaps do not represent a lack of deposition, but a reduction in the variety and abundance of organisms capable of leaving durable remains. Within this quieter world, life persisted in forms that required less structure and fewer resources. Microbial communities, once dominant in the earliest stages of the planet's history, expanded again, occupying spaces that more complex organisms could no longer maintain. These microscopic forms thrived in conditions that had become restrictive to others, their metabolic pathways allowing them to function where oxygen was limited and chemical balances had shifted. The seafloor, no longer shaped by extensive reefs or dense assemblages of larger organisms, reflected this simplification. Sediments accumulated with fewer interruptions, their surfaces less altered by movement, feeding, or construction. The vertical layering that had once supported diverse interactions gave way to flatter, more uniform environments where the complexity of structure was reduced. Energy continued to flow through the system, but along shorter and less intricate pathways. With fewer species occupying distinct roles, the connections between producers, consumers, and decomposers became more direct. This simplification allowed the ecosystem to function under constrained conditions, but it also limited the range of interactions that could occur. The diversity of strategies that had once characterized marine life was replaced by a narrower set of possibilities. In the water above, activity persisted at a subdued level. Organisms that could tolerate fluctuations in oxygen and chemistry maintained their presence, though often in reduced numbers. Movement, feeding, and reproduction continued, but without the density or variation that had defined earlier periods. The ocean did not become empty, but its rhythms slowed and its patterns became less varied. The dominance of microbial life during this time reflects a return to more fundamental modes of existence, where simplicity offered resilience. These organisms did not rely on complex structures or specialized interactions, allowing them to persist across a range of conditions. Their presence stabilized certain processes, contributing to the gradual rebalancing of the system over extended periods. Fossil evidence from this interval captures this transition through what is not found as much as through what remains. The reduction in diversity, the scarcity of complex forms, and the prominence of simpler life all point to a phase where the ocean's capacity for supporting varied ecosystems had been diminished. Within this subdued state, the foundations for future recovery were quietly maintained. The processes that sustain life continued, even in simplified form, preserving the potential for complexity to return when conditions allowed. The ocean, though quieter and less varied, remained active beneath its surface, carrying forward the essential functions that would support the gradual reemergence of more intricate systems. In the aftermath of such extensive loss, persistence depended less on dominance and more on flexibility, as the few lineages that remained carried traits suited to unstable and constrained conditions. These survivors were often smaller in form, requiring fewer resources and capable of reproducing more quickly, allowing their populations to recover even when environments remained unpredictable. Their simplicity did not reflect a lack of potential, but a capacity to endure where more specialized structures could not be sustained. Among these resilient groups were ammonoids, whose coiled shells continued to appear in the fossil record despite the reduction of many other marine organisms. Their ability to regulate buoyancy, combined with reproductive strategies that produced numerous offspring, allowed them to expand into available spaces as conditions stabilized. Variation within their forms began to reemerge, with changes in shell shape and ornamentation reflecting the gradual return of ecological differentiation. Early shark lineages also persisted through this interval, their cartilaginous skeletons and adaptable feeding strategies contributing to their survival. These fishes did not depend on rigid structures that might be compromised by changing chemistry, and their sensory systems allowed them to navigate environments where visibility and conditions varied. Their mobility enabled them to access different regions of the ocean, reducing reliance on any single habitat. The populations that endured during this time carried with them a reduced range of genetic diversity, a consequence of the severe bottlenecks imposed by widespread extinction. With fewer individuals representing each lineage, the variation available for future adaptation was limited, shaping the direction of evolution in subtle ways. These bottlenecks did not prevent recovery, but they influenced which traits would persist and how new forms would emerge. As these survivors expanded, they began to occupy roles that had once been filled by other groups, adapting their behaviors and structures to meet the demands of newly available niches. This process unfolded gradually, with small changes accumulating over generations, allowing lineages to diversify once again. The simplicity that had supported survival became a foundation upon which greater complexity could be rebuilt. Interactions between these organisms remained less intricate than in earlier periods, but they began to increase as populations grew. Predatory relationships reformed, competition returned, and the flow of energy through the ecosystem became more varied. Each expansion introduced new connections, gradually restoring the networks that had been reduced. The presence of these survivors demonstrates how resilience often lies in adaptability rather than specialization. Their ability to persist through changing conditions allowed them to carry life forward, bridging the gap between collapse and recovery. Though diminished in diversity, they held the potential for renewal within their continued existence. Through their gradual expansion and diversification, these lineages set the stage for the reestablishment of more complex marine ecosystems. The ocean, though still recovering, began to support increasing variation once again, guided by the traits that had allowed these organisms to endure when so many others could not. Patterns that would endure far beyond this era began to settle into place, not as sudden innovations, but as arrangements that proved stable across changing conditions. The ocean, still carrying the memory of loss, reorganized around structures and relationships that could persist, forming a foundation upon which later ecosystems would be built. These patterns did not replicate what had come before, but established a new direction shaped by resilience and adaptation. Reef systems returned in a different form, constructed by organisms that could operate within the altered chemistry of the sea. Early coral relatives, along with other reef-building species, began to assemble frameworks that once again introduced structure to the seafloor. These formations grew gradually, layer upon layer, creating environments where diverse communities could gather. Though not identical to earlier reefs, they restored the principle of habitat construction, where life shaped its surroundings in ways that supported further complexity. Within the water column and along the seafloor, vertebrates began to occupy more prominent roles. Fishes, with their internal support structures, refined movement, and varied feeding strategies, expanded across multiple environments. Their ability to combine mobility with adaptable behavior allowed them to interact with a wide range of organisms, influencing the flow of energy through the ecosystem. This shift did not eliminate other groups, but it altered the balance, placing vertebrates in positions where they could shape interactions more consistently. The integration of these elements created systems that were both complex and flexible. Food webs developed with multiple pathways, allowing energy to move through different routes depending on conditions. This redundancy provided a measure of stability, enabling ecosystems to withstand fluctuations without collapsing entirely. The lessons of earlier disruptions were reflected in these structures, favoring arrangements that could adapt rather than those that depended on narrow conditions. Over longer spans of time, these changes influenced the direction of evolution in subtle but lasting ways. Traits that supported versatility, such as efficient movement, varied feeding strategies, and tolerance to environmental variation, became more widespread. Organisms that could adjust to changing conditions had greater opportunities to persist and diversify, shaping the composition of future ecosystems. The ocean's organization began to resemble patterns that would continue into later periods, where structured habitats, active vertebrate communities, and interconnected food webs formed the basis of marine life. While the specific species would change, the underlying framework remained recognizable, carrying forward the principles established during this phase of recovery and reinvention. These developments did not mark an endpoint, but a continuation of processes that had been refined through both expansion and collapse. The structures that emerged were not fixed, but capable of further change, responding to new pressures as they arose. In this way, the ocean carried forward a blueprint, not as a rigid design, but as a set of relationships and patterns that could support life across a wide range of conditions, shaping the future of marine ecosystems in ways that extended far beyond their origin. What once filled the ocean with unfamiliar shapes has left behind no living continuation, not because those forms lacked success, but because success itself does not guarantee permanence. The bodies that once moved through these waters, with structures that now seem distant and unrecognizable, belong to lineages that followed paths eventually closed by change. Their disappearance reflects a process that unfolds across all of life, where persistence depends not only on present conditions, but on the ability to adapt as those conditions shift. Many of the early body plans that defined the Paleozoic seas existed within a range of possibilities that later environments would no longer support. Structures that were effective under specific combinations of chemistry, temperature, and ecological interaction became less viable as those factors changed. Some forms relied on particular balances that, once altered, could not be regained, leading to gradual decline rather than immediate replacement. As ecosystems reorganized through cycles of expansion and collapse, new lineages emerged with traits that aligned more closely with prevailing conditions. This process of evolutionary turnover did not occur as a direct competition between old and new, but as a series of adjustments where certain characteristics proved more adaptable. Over time, these traits became more widespread, shaping the composition of life in ways that differed from earlier configurations. The disappearance of dominant groups illustrates how positions within an ecosystem are not fixed. Apex predators, reef builders, and other influential organisms may define a period, yet their roles can be filled by different forms as circumstances evolve. The functions remain, but the organisms that perform them change, reflecting the dynamic nature of ecological systems. Extinct body plans often represent branches of evolution that explored possibilities not carried forward. Their forms, preserved in the fossil record, reveal combinations of structure and function that once operated effectively, even if they did not persist. These designs contribute to the broader history of life, demonstrating the range of solutions that have been tested over time. Environmental change plays a central role in determining which lineages continue and which do not. Shifts in climate, chemistry, and geography alter the conditions under which organisms live, favoring some traits while limiting others. Adaptation can extend the presence of a lineage, but when changes exceed its capacity to adjust, extinction follows as part of the ongoing process. The absence of these ancient rulers does not indicate a failure, but rather a transition within a system that is constantly reshaped. Each period of dominance is temporary, defined by conditions that will eventually give way to new arrangements. The ocean carries forward the influence of these past forms through the traits and structures that persist, even as the organisms themselves disappear. Through this continuous cycle, life maintains its capacity for change, allowing new forms to arise and occupy roles once held by others. The patterns observed across these transitions reveal that stability is always provisional and that the diversity of life depends on the constant interplay between persistence and replacement, shaping a world where no single form remains forever. The shapes that once filled these waters would feel unfamiliar if seen again, their forms carrying arrangements that no longer exist, their movements guided by structures that have no direct counterpart today. Yet the strangeness was never separate from the continuity that followed, because those early designs, however temporary, contributed to the unfolding of everything that came after. What appears distant now was once the present state of life, as complete and functional as any that would replace it. Across these long intervals, nearly every major lineage that defines complex life began within this shifting ocean. The earliest versions of bodies that would later walk, swim, burrow, or fly all trace their origins to these waters, where structure and function first aligned in ways that could be carried forward. Even as individual forms disappeared, the underlying patterns persisted, reshaped and refined across time, linking the past to the present through a continuous thread of adaptation. The ocean acted not as a passive setting, but as an active force, shaping possibilities through its chemistry, its movement, and its vast range of environments. Each change in temperature, composition, or circulation altered the conditions under which life could exist, guiding evolution without intention, yet with profound effect. Within this environment, life responded, adjusting its forms and behaviors to match the shifting context, creating a dynamic exchange between organism and world. The rulers of each period emerged from this interaction, defined by traits that suited the moment, whether strength, speed, flexibility, or resilience. Their dominance reflected a balance that could be maintained only while conditions remained within certain limits. As those limits changed, new forms rose, carrying different combinations of traits that aligned with the evolving system. The transitions were not abrupt replacements, but gradual shifts, where influence passed from one lineage to another. Through all of these changes, the ocean itself endured. Its surface altered, its chemistry shifted, its inhabitants changed. Yet it remained the medium through which life developed its earliest complexities. The continuity of the sea provided a foundation upon which variation could unfold, allowing each phase of life to build upon what had come before, even as specific forms disappeared. What remains today carries the imprint of those earlier worlds, not in direct repetition, but in the structures and relationships that persist. The way organisms move, interact, and adapt reflects patterns first established in those ancient waters, refined through countless generations. The unfamiliar creatures of the past are not separate from the present, but part of a lineage that continues in altered form. In this sense, the ocean holds a record not only in stone, but in the living systems that trace their origins back through time. The diversity seen now is shaped by a history of change, where each phase contributed to the possibilities that followed. The sea continues to move, to shift, to sustain, carrying forward the processes that once gave rise to forms so strange, yet so essential to everything that exists today.